Okay, let's get into it. Number 10. The Grand Tack. Picture the solar system as it is now. Neat. Orderly. 8 planets running their laps in almost circular lanes. Jupiter sitting out past the asteroid belt like a bouncer who never leaves his post. It feels permanent. It feels like it was always this way. It probably wasn't. There's a model published in Nature back in 2011 by Kevin Walsh, Alessandro Morbidelli, and their colleagues that says the young Jupiter didn't stay put. It wandered. When the sun was still surrounded by a thick disk of gas and dust, Jupiter carved a gap in that disk and started spiraling inward, drifting toward the sun until it reached about 1.5 times Earth's distance from the sun. That's roughly where Mars orbits today. A gas giant, 300 times the mass of Earth, cruising through the inner solar system like a wrecking ball on a slow swing. And then it turned around. Saturn, forming a little later, caught up, locked into a gravitational rhythm with Jupiter, and the two of them reversed course and sailed back out to where they live now. Sailors have a word for changing direction against the wind. They call it tacking. So this idea got a name, the Grand Tack. Here's the thing. If Jupiter really did this, it explains a couple of mysteries that have been bugging astronomers for years. Take Mars. Mars is a runt. It's only about 1/10 of the mass of Earth, which is strange, because the models say it should have grown much bigger. But if Jupiter swept through that region first, it would have scattered most of the building material away, starving Mars before it could bulk up. A small Mars isn't a coincidence. It's a fingerprint. Then there's the asteroid belt. It's not one clean population. It's a weird mix. Dry, rocky bodies from the inner solar system, tangled up with icy, primitive bodies from way out past the giant planets. That's exactly the mess you'd expect if Jupiter plowed through, flung everything around, and then dragged a second batch of material back inward on its way home. Now, to be fair, this isn't settled. There are rival models with their own migrations and their own scrambled belts. But the picture underneath is hard to shake. The calm, clockwork solar system you were taught about had a wild adolescence, and the empty gap where Mars stayed small might be the scar the biggest planet left behind when it wandered in, and then quietly wandered back out. Number 9. The rare Earth hypothesis. We tend to assume the universe is teeming. 100 billion galaxies, each with 100 billion stars, most of them wrapped in planets. Run the numbers and it feels obvious. Somebody's out there, probably lots of somebodies. In the year 2000, 2 scientists pushed back hard on that instinct. Paleontologist Peter Ward and astronomer Donald Brownlee wrote a book called Rare Earth, and their argument was careful and unsettling. They didn't say life is rare. They said complex life is rare. Microbes, maybe everywhere. Animals, almost nowhere. Their point was that getting from pond scum to anything that can move, think, or build takes an absurd run of good luck. And not one lucky break. A whole chain of them, all holding at once for billions of years. Start with location. Ward and Brownlee argued there's a galactic habitable zone, a band in the galaxy that isn't too crowded with exploding stars and isn't too starved of the heavy elements you need to build a rocky world. Too far in, you get cooked and sterilized. Too far out, there's not enough material. Earth sits in the sweet spot. Then, the star. Ours is stable, middle-aged, and quiet, burning steadily for billions of years without the violent flares that would scour a planet's surface. Plenty of stars don't offer that. Then, the planet itself. Plate tectonics, recycling carbon, and stabilizing the climate over deep time. A magnetic field, deflecting radiation, and a big one, literally. The moon. Our absurdly large moon steadies the tilt of the Earth, keeping the seasons from lurching into chaos. And then there's Jupiter, out on the edge, its gravity mopping up or flinging away comets and asteroids that might otherwise have slammed into us again and again. Line all of that up. Right galaxy, right neighborhood, right star, right size, right moon, right giant guardian. Each one, on its own, maybe not so unlikely, but all of them, together, on the same world, for long enough, that's where the number starts to collapse towards zero. If Ward and Brownlee are right, it reframes the silence. We keep asking where everybody is. Rare Earth's answer is quiet and a little cold. Maybe the microbes are chattering away on a billion worlds. And maybe the kind of luck that turns slime into stargazers is so specific that it barely ever happens twice. Which would mean the strangest thing in the sky tonight isn't out there at all. It's the ground under your feet. Number 8. Quantum Darwinism. Here's a question so basic it sounds silly. Why do we all agree on what's real? You and I look at the moon, and we see the same moon. Same shape, same position, same craters. That sounds trivial until you remember what quantum mechanics says about the world underneath. Down at the smallest scale, particles don't have definite properties until they're measured. They exist in blurry combinations, here and there, this and that, all at once. So how does a fuzzy quantum world produce a solid, shared reality that billions of observers all read the same way? Physicist Wojciech Zurek at Los Alamos has an answer, and it borrows its logic from Darwin. He calls it quantum Darwinism. The idea goes like this. A quantum object is constantly being touched by its environment. Photons bounce off it. Air molecules bump into it. Every one of those interactions is like a tiny measurement, and it copies information about the object out into the surroundings. But not all information survives. Most quantum states are fragile. The moment the environment touches them, they smear out and disappear. Only certain robust states, what Zurek calls pointer states, survive the contact and get copied. And here's the beautiful part. They don't get copied once. They get copied thousands of times, stamped redundantly all over the environment. So when you look at the moon, you're not measuring the moon. You're intercepting a tiny fraction of the countless identical copies of the moon's information that are already flooding the space around it. I intercept a different fraction. We both read the same story because the environment has plastered that story everywhere. Objectivity in this picture isn't a given. It's a survival contest. The states that get broadcast the most redundantly are the ones that become real for everyone. The fragile alternatives, the roads not taken, leave no copies at all. They don't get overruled. They just vanish, unrecorded. And this isn't only philosophy. Around 2018 and 2019, experimental groups started testing it. One team, working with a nitrogen defect inside a diamond, and others working with photons, looked for exactly this redundant copying and found the signatures the theory predicted. So the solid world you trust, the shared reality you never question, might be solid for a strange reason. Not because it's fundamental, but because it's the most heavily plagiarized version of events, copied so many times that no one can see anything else. Reality, it seems, is whatever the universe decided to write down the most. Number 7. Extra dimensions. You live in 3 dimensions of space. Left and right, forward and back, up and down. Add time, and that's the whole stage. 4 dimensions. Everything you've ever seen or touched happens inside them. String theory says that's not the whole stage. Not even close. The idea started as an attempt to solve the deepest problem in physics. Our 2 best theories, quantum mechanics for the very small and general relativity for the very large, don't get along. Try to force them together, and the math spits out nonsense. String theory offered a fix. What if the fundamental things in the universe aren't tiny points, but tiny vibrating strings? Different vibrations would give you different particles, the way different notes come off one guitar string. One elegant idea, generating the whole particle zoo. There was just one catch. For the math to work, for the strings to vibrate consistently without breaking the rules, the universe can't have 4 dimensions. It needs 10. In the extended version, called M-theory, it needs 11. So where are the extra 6 or 7? We've never seen them. We've never bumped into a spare direction while parking the car. The answer string theorists give is that they're curled up, compactified, folded so tightly that they're wrapped up at every single point in the space you already know. Imagine a garden hose seen from far away. It looks like a line, one-dimensional. Get close, and you see the surface curls around into a second dimension you couldn't detect from a distance. Now do that 6 times over, at every point in space. With a shape so small, no experiment we have can probe it. In 1985, physicists including Edward Witten and Andrew Strominger worked out that these hidden dimensions could take the form of intricate geometric shapes, called Calabi-Yau manifolds. Folded, twisted, beautiful little pockets of extra space, threaded invisibly through the world. And here's where it gets both wonderful and frustrating. There isn't one shape. There are a staggering number of possible Calabi-Yau geometries, and string theory doesn't tell you which one is ours. This is the famous landscape problem, and it's why critics push back hard. A theory that can be folded almost any way struggles to make a single prediction you can test. But sit with the core claim for a second. If string theory is right, then reality is 6 dimensions, richer than it appears. Not somewhere far away. Right here. In the space between your hands, curled too small to ever see, an entire hidden architecture might be holding everything together. Number 6. Pilot wave theory. Quantum mechanics has a reputation, and it earned it. The standard story says the world at its smallest scale is fundamentally random. A particle doesn't have a definite position until you look. Reality is a roll of the dice, and even God, in Einstein's famous complaint, seems to be gambling. Einstein hated that, and it turns out there's another way to read the same equations, one where the dice are a mirage. It's called pilot wave theory. Louis de Broglie sketched it out in 1927, then abandoned it under pressure from his colleagues. David Bohm revived it in 1952, and a stubborn minority of physicists have carried it ever since. The picture it paints is almost comforting. In pilot wave theory, particles are real. They're actual, definite objects with actual, definite positions at every moment, whether you look or not. But they don't travel alone. Each particle rides on a wave, a real physical wave that fills space and guides its motion. The wave is the pilot. The particle just goes where it's steered. And here's the elegant part. This theory predicts exactly the same experimental results as standard quantum mechanics. The famous weirdness, the interference patterns, the way particles seem to go through 2 slits at once, all of it still happens. But there's no fundamental randomness in the mechanism. The apparent chance is just our ignorance of the particle's precise starting point and the shape of its guiding wave. Underneath, everything is determined. For decades, this sounded like pure philosophy, untestable, a matter of taste. Then, in 2005, 2 French physicists, Yves Coudet and Emmanuel Fort, did something that made people sit up. They took a tray of silicone oil, vibrated it, and let tiny droplets bounce across the surface. Each bouncing droplet generated ripples, and those ripples pushed the droplet along, a particle, riding its own wave. And these walking droplets started doing things that were supposed to be impossible for anything so ordinary. They diffracted. They seemed to tunnel through barriers. Sent through a gap over and over, they built up statistical patterns that looked eerily quantum. A little classical system, out in the open on a lab bench, mimicking the behavior we thought was unique to the subatomic world. Now, the droplets aren't a perfect copy of quantum mechanics, and the theory has real costs, especially a deep non-locality that troubles a lot of physicists. It's still very much a minority view, but it plants a seed of doubt that's hard to uproot. Maybe the universe isn't rolling dice after all. Maybe it just never let us see the wave doing the steering. Number 5. Emergent gravity. Gravity feels like the most fundamental thing there is. It holds you to the floor. It holds the moon to the earth, and the earth to the sun. Newton described it. Einstein reimagined it as the bending of space-time. And for centuries, we've treated it as one of the basic forces woven into the fabric of the cosmos. In 2011, a Dutch physicist named Erik Verlinde suggested something that sounds almost heretical. What if gravity isn't fundamental at all? What if it's not a force in the deep sense, but a side effect? An emergent property, something that appears out of statistics, the way heat appears out of jiggling atoms. Think about temperature for a second. There's no such thing as a single hot atom. Heat isn't a fundamental property of one particle. It emerges when you have trillions of them moving around, and it only makes sense at that scale. Verlinde's claim is that gravity might be the same kind of thing, not a basic ingredient of reality, but a bulk effect that shows up when you account for information and entropy in space. Entropy is, roughly, a measure of disorder, of how many ways you can arrange the hidden pieces of a system. Verlinde built on deep results, linking entropy to the surface area of regions of space, ideas that come out of black hole physics. And he showed that if you assume space stores information this way, you can derive Newton's law of gravity from it. The inverse square law, the way gravity weakens with distance, falls out naturally because area grows with the square of distance. Gravity, in his math, is space-time relaxing toward higher entropy. Objects fall not because a force tugs them, but because the information content of space nudges them along. And then he pushed further. In 2016, Verlinde argued that this emergent picture produces a little extra gravity in galaxies, exactly where astronomers currently invoke dark matter to explain why galaxies spin faster than they should. If he's right, dark matter might not be a mysterious, invisible substance at all. It might be a leftover of the way spacetime is stitched together from information. Now, this is contested hard. Other physicists have tested his formulas against clusters of galaxies and dwarf galaxies and argue they don't hold up. It's not a finished theory. It's a provocation, but it's a profound one. Because if Verlinde is even partly right, then the ground you're standing on isn't held together by a fundamental force. It's held together by information, by entropy, by the universe doing bookkeeping. And gravity is just what that bookkeeping feels like from the inside. Number 4, Superdeterminism. This one comes with a warning because it asks you to give up something you may not want to give up. Start with the strangest result in physics: quantum entanglement. You take two particles, link them, and send them light years apart. Measure one, and the other instantly reflects the result. Einstein sneered at it, calling it spooky action at a distance, because it looked like information leaping across space faster than light. In 1964, physicist John Bell proved something powerful about this. He showed that no theory based on local hidden variables, no theory where particles carry secret instructions, and nothing travels faster than light, could reproduce the quantum predictions. Experiments have tested Bell's result over and over, and quantum mechanics wins every time. The usual conclusion is stark. The universe is either genuinely random or genuinely non-local, or both. But Bell's proof rested on a quiet assumption, one almost nobody noticed at first. He assumed that the experimenter's choice of what to measure is independent of the particles being measured. That when you decide to turn your detector this way instead of that way, your decision has nothing to do with the hidden state of the particle flying toward it. Superdeterminism says, what if that assumption is false? The physicist Sabine Hossenfelder is its most prominent modern defender. Her point is subtle. If the settings you choose and the particle you measure were correlated all along, secretly linked by the shared history of a fully deterministic universe, then you can build a theory that's local, keeps hidden variables, and still matches every quantum experiment. The spookiness dissolves. There's no faster-than-light influence. There's just a cosmos where nothing is truly independent of anything else. The catch is enormous, and it's why most physicists recoil. Superdeterminism means your choice to measure a particle one way rather than another was never fully free. It was baked into the initial conditions of the universe, tied to the very thing you were about to observe. Critics call it conspiratorial, a universe rigged to fool us. Hossenfelder counters that we only call it a conspiracy because we're attached to the idea of our own independence, and that general relativity is local, so maybe locality is worth keeping. It remains a minority view, and a genuinely uncomfortable one, but it's the last unclosed loophole in Bell's theorem, and no experiment has ruled it out, because in principle, no experiment can. To test it, you'd need a truly free choice, and that's exactly the thing superdeterminism says you never had. Number 3. The universe from nothing. Every origin story runs into the same wall. However far back you push, you eventually hit the question that has no comfortable answer. Why is there something rather than nothing? What came before the beginning? In 1982, the physicist Alexander Vilenkin proposed an answer that's either deeply satisfying or deeply maddening, depending on your mood. The universe, he suggested, created itself. It tunneled into existence out of nothing. To feel why that's not just poetry, you need one piece of quantum mechanics: quantum tunneling. In the quantum world, a particle can pass through a barrier it doesn't have the energy to climb over. It's stuck on one side. And then, with some probability, it's simply on the other side, having crossed a wall it could never surmount. This isn't speculation. It's how the sun shines. It's how certain radioactive atoms decay. Tunneling is routine, everyday quantum behavior. Vilenkin's move was audacious. He took that same mathematics and applied it not to a particle, but to the entire universe. In his model, a tiny closed universe can tunnel out of a state with no space, no time, and no matter, into a small bubble that then begins to inflate and grow into the cosmos we live in. There's no Big Bang singularity, no infinitely dense point where the equations break down. And crucially, the model needs no initial conditions, no rules dialed in beforehand, because there is no beforehand. And this is where people fight. Because when Vilenkin says nothing, he means nothing in a very specific sense. No space, no time, no matter or energy, a genuine absence. The universe, in his picture, is a quantum fluctuation that didn't have to happen, tunneling into being on its own. Critics, including philosophers, push back hard. They argue that this nothing isn't truly nothing, because it still assumes the laws of quantum mechanics, still assumes a mathematical framework in which tunneling can occur. And that's fair. A quantum nothing that follows rules is not the same as absolute non-existence. There's also a deep, unresolved argument about which boundary condition is correct: Vilenkin's tunneling version, or the rival no-boundary proposal from James Hartley and Stephen Hawking. We can't test any of this. Not yet. Maybe not ever. But something about it lingers. The idea that the entire cosmos, every galaxy, every star, every person who has ever lived might have begun the way a single particle slips through a wall. Not with a bang commanded from outside, but as a quiet, uncaused quantum accident that tunneled its way into being and never looked back. Number 2. The many worlds interpretation. Here's the thing about quantum mechanics that no one has ever fully explained: the measurement problem. When a particle is left alone, the equations describe it as a spread of possibilities, all coexisting. here and there, spin up and spin down. But the instant you measure it, you only ever see one outcome. The spread of possibilities seems to collapse into a single answer. And the standard textbook version of quantum mechanics just, well, asserts that. It puts collapse in by hand, a special rule that kicks in when a measurement happens. But nobody can say what counts as a measurement, or why the collapse occurs, or where the other possibilities go. In 1957, a young physicist named Hugh Everett looked at that awkward extra rule and asked a simple, radical question. What if it isn't there? What if the collapse never happens at all? Take the equations completely literally. Don't add anything. If you do that, then when you measure a particle that's in two states at once, you don't force it to pick one. Instead, you become part of the system. You split. One version of you sees the first outcome. Another version of you sees the second. Both are equally real. The universe branches quietly, and every possible result happens, each in its own separate world. That's the many worlds interpretation. And the thing people get wrong about it is that it sounds like the most extravagant idea in physics, when in fact, it's the most economical. Everett didn't add parallel universes to the math. He removed a rule. The parallel worlds are just what the equations describe, if you stop hiding from them. It got a cold reception at first. Everett took it to Niels Bohr, the grand old man of quantum theory, and got brushed off. Discouraged, Everett left academia, but the idea refused to die. And today, helped by our modern understanding of decoherence, which explains why those branches stop interfering and go their separate ways, many worlds is taken seriously by a lot of working physicists. People like David Deutsch and Sean Carroll defend it openly. Now follow it to the end. If it's right, then every quantum event that could go two ways splits reality in two. And that's happening constantly, everywhere, in every atom, which means there are countless versions of this exact moment. Countless versions of you, branching off with every flip of the quantum coin, living out every choice you didn't make. Not in some far-off galaxy, right here, in the same space you occupy, just in a world you can no longer reach. Number 1. The mathematical universe. There's an old puzzle that physicists like to call the unreasonable effectiveness of mathematics. It's this. Why does math work so absurdly well at describing the universe? You scribble some equations on a chalkboard, pure abstraction, and somehow they predict how galaxies rotate and how light bends and where a planet will be in 1,000 years. Why should the cosmos care about our symbols? Why does reality obey math at all? The cosmologist Max Tegmark at MIT has an answer that is either the deepest idea on this list or the strangest, and honestly it might be both. His answer is that math works so well at describing reality because reality is not described by math. Reality is math. He calls it the mathematical universe hypothesis. He laid it out in a 2007 paper and expanded it in his 2014 book, Our Mathematical Universe. And the claim is exactly as radical as it sounds. The universe isn't a physical thing that happens to follow mathematical laws. The universe is a mathematical structure. Full stop. The particles, the forces, the space, the time, all of it are features of one enormous mathematical object, and we are self-aware patterns living inside it. Sit with that. When you feel the weight of your own body, when you see the color red, when you remember someone you love. Tegmark is saying that all of it is what a particular piece of mathematics feels like from the inside, not represented by math, made of it. And then he takes the final step, the one that makes mathematicians dizzy. If our universe is just one mathematical structure, why would it be special? Every logically consistent mathematical structure, he argues, exists in exactly the same way ours does. Every consistent set of equations is a universe, real, populated perhaps by its own self-aware patterns, wondering why their math works so well. Existence, in this view, is nothing more than logical consistency. If it doesn't contradict itself, it's out there, somewhere, being a world. It's almost impossible to test, and plenty of physicists say that disqualifies it as science. The critic Jürgen Schmidhuber points out you can't even assign sensible probabilities across infinitely many mathematical structures. Fair enough. Maybe this is philosophy wearing a lab coat, but it leaves you standing somewhere very strange. Because if Tegmark is right, then the ground beneath everything, the final answer to what the universe is made of, isn't particles, isn't energy, isn't space. It's an idea. A structure so perfectly consistent that it doesn't just describe a reality. It is one, and you're inside it, right now, reading its equations from within. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.